1005, yes. So Q equals 1005, P equals 1004 because their difference is only 1. Q minus P equals 1. So that's one solution for this equation of n squared plus 2009n equals n plus 2009n equals a squared. Okay, so one second. Okay, so the second scenario for this equation that we remember is n plus k equals a squared equals n times n plus 2009. Yes. So I'll show you why this case is impossible. Let's examine these two numbers, n times n plus 2009. Hypothetically, say n is made up by a bunch of numbers, a times b times c times d. Actually, we've already used a. Let's not use that. N equals a bunch of numbers timed together. N plus 2009 is also a bunch of numbers timed together. The first thing I want to show you is that these two numbers are co-prime or common factor of 2009 between these numbers. So why is that? Let's say that they have a common factor, which is p, just say p, and n equals, let's say, p times q1. N plus 2009 equals p times q2 because, well, there are different quantities timed by that number. They are the common factor of 2009 and, a common factor of n and n plus 2009, which means that n plus 2009 minus n, so the second one minus the first one, that would be q2 minus q1, that times p, which means 2009 equals some other quantity q3, let's say, times p. So what does that tell us? That tells us that 2009 is this common factor between n and n plus 2009 times another quantity. However, we know that 2009 itself is a prime. That means this case, either p is 1, 2009, or just simply there's no other cases. That's impossible. If n and n plus 2009 are not co-prime, that means this p, this common factor between them, is 2009. However, if they are co-prime, then it's 1. If it's other cases, it's impossible. So there are only these two cases. After knowing that n and n plus 2009 are co-prime, how do we get to the fact that they cannot make up as a square number? Well, if we know that n times n plus 2009 is co-prime, that means all the factors of n cannot find a reciprocal factor in n plus 2009. So it differs from the first case where n equals p squared, n plus 2009 equals q squared. Well, I said the other way around, but you get the idea. Let's say right now that n equals p1 times p2 times p3. I know I used a lot of p and q's, so, well, please don't be confused by that. And p4 times p5, blah, blah, and n plus 2009 equals p1, q1, oh my gosh, what's wrong with me today? Q1, Q2, Q3, Q4, Q5, da 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 da. So having these two different products, say that n has found a bunch of like matching numbers that multiply together to make up for some random number squared, right? Let's say c squared or something. And at the end, you have one number remaining, which is p3. Now, p3 cannot find a match within n itself. p3 can't find a match in the pile of q's either, because all the q's, all the product of any of them is co-prime to all the products of any of the p's. because we know that n plus 2009 and n, they're coprime, meaning that they have only 1 as their biggest common denominator. Therefore, having always this isolated P3 right here, that means n and n plus 2009 together cannot be a square number, because for it to be a square number, all of the factors of which has to be cleanly grouped into 2 different piles, where one you have P1, the other one must have another P1. If you have P5, the other one also have a P5. All these numbers, and you can't have like a P3 here, but then you can't find a number that is equivalent to P3 and is coprime to all the other numbers. So having this unique factor just prohibits the value of n times n plus 2009 to be a square number. And since we have proven the second case impossible, we only have the first case, which only yields one solution: q equals 1005 and p equals 1004. And that concludes the first solution. The second solution is, well, it looks a lot shorter, a lot shorter, and it seems a lot easier, but it's, well, for me, it was the, I didn't think of this as my first choice. I actually took some time to think about the algebra first, and eventually I got the second solution. So let n squared plus 2009n equal a squared. Again, this means 4 times n squared plus 8036n, well, that 2009 times 4, equals 4a squared. What does this mean? This means that 2n plus 2009 squared minus 4a squared equals 2009 squared. And this gives us, actually, 2n plus 2009 minus 2a times 2n plus 2009 minus 2a, plus, that equals 2009 squared. And to make up for this 2009 squared, these two different numbers, they can't both be 2009. So the first one has to be 1. The second one has to be 2009 squared, because you can't find any other combination of number that multiplies to 2009 squared, because 2009 itself is a prime number. So since 2n plus 2, well, I mean, you get the idea. After solving these two equations, you get n equals 1004 squared. And that is the case. And somehow I noticed that it is different from what I had before. What the heck? Is it 1004 squared or was it 1004? Oh, never mind. Yes, sorry. Q, okay, before, okay, sorry. Q, it was 1005, N was 1004. So, sorry, P was 1004. So N actually equals P squared, as we said before. N plus 2009 actually equals Q squared. That equals 1004 squared, and this one equals 1005 squared. So that's how you solve the problem. And I am sorry for the constant incoherence of my speech while I present to you the solution that are completely genuine and cost me like an hour to film this. So, alright, thank you very much. Peace out.